Hey guys, Professor Doney back again, continuing with vertical motion. Today we're going to look at another type of vertical motion problem that's one-dimensional, just up and down. We did drop, we did throw down, we did throw up. Now we're going to throw up the object with some initial velocity, and we're going to wait until it goes up and it reaches its peak, and then it starts to come back down. Okay. Now it may come back down all the way back to our launch height, or it may come back down and land on a roof or something above, or it may come back down to us and pass us and actually go down beyond us or below us. So we're going to talk about the three different types there. For now, we'll just talk about throw up and back down, and we'll say it comes to the same height. Same height meaning it's going to launch from here or throw up from here, and it comes back to that same place. So its final displacement would be 0 and go from there. So these are very similar to throw ups. We're going to still pick gravity down. At the peak, we know that the velocity goes to 0, the final velocity at the peak. Gravity, though, continues to pull on the object, which is why it slows down, decelerates to 0, and then they start to accelerate and speed up as it falls back down. What we're going to take advantage of, though, in this problem is if it goes up and comes back down to the same height, that's my same height there, is we have some symmetry going on. The object's going to go up, decelerate because of gravity is in the opposite direction, and then it's going to come back down. Gravity is going to accelerate it. Because of this symmetry and doing the problems of we can find the time up and that, we find out that the time to go up equals the time to fall back down. And also the distance it goes up equals the distance down. And even more, the velocity that we throw it with here at the beginning will equal the velocity it hits with here, just in the negative direction. So if we throw it up with VO, it actually lands with VO in the negative direction. So we can find the total air time by just finding time up and doubling it. So to do this kind of problem, we looked at the last one, we threw it up at 20. And let's find a bunch of different things there. If we use that first equation, V equals VO plus GT, again we're still calling positive up, and gravity is down. Let me change colors here. We'll get 0 at the peak, 20 up plus minus 9.8 times t, and we saw in the last problem that t equals roughly about 2 seconds. Okay. That means if it took 2 seconds to go up and stop, if it falls back down the same distance, the time down will also be 2 seconds. So our total air time, put up here, or hang time or time in the air, would be 2 plus 2, or 4 seconds. Now we could go through and throw it up and then look at the second half as being a drop problem, but if we know it comes all the way back down, we can just drop it from that height. So we know how to find out how far it went up and all that. What else can we find on here? We can find out where it is after, see if it takes 4 seconds to go up total and come back down. Where is it after 3 seconds? Well, we can go to our third equation. We're still going to call positive up because we're throwing it up. Our initial is going to be 20. We say 3 here, plus half, minus 9.8, 3 seconds squared. If we go through that mess, that comes out to be 60. 60 minus roughly, what's that, 9, 40, just under 45. Say 44-ish, that gives us about 16 meters. Since that number is positive, it's telling us that it is still 16 meters above the ground. So we threw it up, it went to its peak, and it started coming back down, and here it is at 16 meters above the ground. If we ended up with a negative number or 0, it means it's at the ground. If it's a negative number, it means it fell below us or it's already been on the ground. So hope that helps. We're going to do some more of those because they can be a little confusing. So check back here next.